The engine in the dark. How the core makes a magnetic shield. To understand why a dent in the sky starts under our feet, go down past crust and mantle to a boundary where rock gives way to metal. At roughly 2,900 kilometers, seismic waves slow sharply. That's the top of the outer core, a global ocean of liquid iron alloy. Deeper still sits the inner core, a solid sphere of mostly iron and nickel, hot as a small star's photosphere and squeezed to metallic order. One phase sloshes, one rings like a bell. Together, they run a power plant that never sleeps. The energy budget is simple and relentless. Heat is escaping the planet. Primordial heat from formation, radiogenic heat from long-lived isotopes, and latent heat released as the inner core crystallizes grain by grain. Hot fluid rises, cooler fluid sinks. Rotation twists those motions. The Coriolis effect organizes the flow into column-like rolls aligned roughly with Earth's spin axis. Wherever a conducting fluid cuts across magnetic field lines, it induces electrical currents. Currents make magnetic fields, and those fields push back on the flow, steering future motions. That feedback loop is the Geodynamo. It's not a neat bar magnet, it's weather in metal. The large-scale time-average field looks like a dipole. Field lines emerging near Antarctica, arcing through space and diving back down near the Arctic. But layered atop that global scaffold are regional lumps. Patches of stronger and weaker flux born from turbulent eddies, shear zones, and boundary conditions at the base of the mantle. The surface field we map is the sum of both, the elegant shape and the mess riding piggyback. 3 ingredients make the loop self-sustain.
First, vigorous convection. Heat and light elements released as the inner core grows make buoyant fluid that wants to rise. Second, rotation. It organizes chaos into helical flows, the geometry a dynamo prefers. Third, electrical conductivity. Liquid iron alloys carry charge easily, so tiny currents amplify in the structure. Remove any one, cool the core too much, stop rotation, or replace iron with syrup, and the loop stutters. Mars likely failed that test long ago. Now, add the middleman that complicates everything, the mantle. It's solid on short timescales, but not uniform. Seismic tomography reveals 2 continent-scale thermochemical provinces perched atop the core, one beneath Africa, the other beneath the Pacific. Where the mantle above is hotter, it insulates. Heat leaks more slowly, and convection below slackens. Where it's cooler, heat escapes faster, and flow intensifies. That patchy heat flux imprints patterns onto the outer core's motions. At the core mantle boundary, you can map regions where field lines point up or down more strongly. Those patches drift, split, and merge over decades to centuries, dragging the surface field along. Meanwhile, the inner core does more than harden. Its growth releases latent heat and light elements into the outer core, fueling buoyancy. Some studies suggest hemispheric asymmetry in that growth, slightly more crystallization on one side, which would nudge convection patterns. Others see torsional oscillations, slow shear waves zipping through the outer core, briefly speeding and slowing zonal flow. Either way, the engine isn't static. It coughs, it clears its throat, it retunes. Why do we care? Because those tangled lines reach into space and grab charged particles by the collar. The magnetosphere, the vast magnetic bubble that envelops our planet, deflects most of the solar wind. Where field lines connect to space, currents flow along them, feeding auroras at high latitudes. Where lines close, they form traps, the Van Allen belts, where energetic particles spiral, mirror, and drift. The inner belt, rich in protons, sits closer to Earth where the field is strong. But the field isn't centered perfectly in the planet, so the belt sags lower over one sector, the South Atlantic. That sag is a downstream symptom of core complexity. The field also breathes with the sun. A southward interplanetary magnetic field locks onto Earth's day side, letting energy in. Reconnection in the tail flings plasma earthward, ionospheric currents surge, and the ground feels those changing fields as voltages induced along long conductors. None of that would matter without the core scaffold. It sets the stage, space weather writes the scene. Picture the loop in action. A plume of buoyant, iron-rich fluid rises along a column aligned with Earth's spin. Twisting motion wraps field lines into helices. Induced currents strengthen the poloidal field,
the long arc from pole to pole, and generate a toroidal component wrapped around like latitude bands. Shear and buoyancy exchange energy between those components in a cycle that keeps rebuilding the large-scale field even as turbulence scribbles on top. The math that captures this magnetohydrodynamics looks forbidding. The intuition is familiar: moving conductor, existing field, induced current, new field. We've tried to bottle that physics. In labs, researchers spin vats of molten sodium inside nested spheres and cylinders. The flows mimic helical motion, and sometimes, briefly, a magnetic field self-excites. It's finicky, too slow and nothing happens, too fast and turbulence kills structure. But it proves the principle: under the right conditions, motion begets magnetism. Two final truths anchor this engine. First, it's resilient. The inner core's growth has likely strengthened the dynamo over the last hundreds of millions of years. Second, it's moody. Uneven heat flow and internal waves let regional features blossom for decades. That's how you get a weak patch over southern Africa that lasts long enough to matter for satellites, and long enough to leave a fingerprint in archaeological clay. So when a satellite reboots over the South Atlantic, that's not space being random. It's the end of a causal chain that starts in a metal ocean. The dent in the sky is the surface echo of weather in the core. And once you've seen the engine, the next question is obvious. What are the knocks and rattles telling us right now? Seismic whispers, what the core slowdown story really means. To hear the core, we listen to quakes that repeat themselves. Not the headlines, literal repeaters. Earthquakes that rupture on the same fault patches, send waves along the same great circle paths, and arrive at the same stations like clockwork. When the source and the path are nearly identical, the tiny differences left over, milliseconds shaved here, a faint wiggle there, become a microscope. The waves that matter for the core have an awkward name: PKIKP. Waves that go through the
Mantle, P. The outer core, K. Pierce the inner core, I, then back out. Their coda, the faint ring down after the main arrival, carries extra hints about scattering and structure along the way. Now stack decades of those twins, and the pattern changes. Through the 199s and early 200s, the PKIKP differentials behaved as if the inner core was super rotating, drifting eastward relative to the mantle by tenths of a degree per year. Then, somewhere around 2008 to 201, the sign flips. The differentials shrink, even reverse in phase. Studies that extended the catalog to 2023, adding fresh South Sandwich Islands repeaters and, yes, Cold War nuclear test pairs as fixed reference shots, found the same story with better timing. The inner core didn't stop. It slowed relative to the mantle and began backtracking, moving westward more slowly than it had previously moved east. Think of two nested gears with a bit of slip. The outer gear, mantle, keeps turning. The inner gear, solid core, speeds up, then eases, then lags by a hair. The nuance matters. This isn't Earth reversing. It isn't even the whole core. The liquid outer core, the dynamo stage, is still sloshing. What's shifting is the solid inner core's tiny differential rotation relative to the crust and mantle above. We're talking minute angular rates on decadal cycles, not a cinematic grind to a halt. Media loves the core stopped, but seismology says it slowed and reversed relative to us, which is less viral and far more interesting. How do waves pick that up? Because iron isn't uniform at those depths. The inner core is anisotropic. Its crystals align preferentially, so waves going north-south travel at slightly different speeds than those going east-west. If the inner core's orientation or our relative angle through it changes, the travel time differences for core crossing phases shift. Repeating quakes keep the source constant. Any residual drift in arrival times points to changing geometry along the path. When multiple paths across Asia-Pacific, across the Americas, across the South Atlantic show consistent trends in PKIKP minus nearby core phases, a global signal emerges. The cleanest stacks show decadal modulation in step, with small wiggles in length of day, a hint that angular momentum is shuffling between the mantle and the core through electromagnetic and gravitational coupling. Why would the inner core backtrack? The same forces that spin it up can slow it down. Electromagnetic coupling. The magnetic field threading the fluid outer core can tug on the solid inner core. Topographic coupling. Tiny bumps at the inner core boundary. Mountains measured in hundreds of meters on a sphere the size of the moon can transmit torque as flows shear across them.
If outer core flow reorganizes, say a torsional oscillation sweeps through, speeding and then slowing zonal motion, the net torque on the inner core changes sign. Over years, that nudge adds up to a phase drift we can measure as seismic time shifts. What nobody knew at the time was how much else had to be changing. Recent analyses suggest the inner core's surface itself may be evolving. Subtle changes in roughness or layering that alter wave amplitudes, not just arrival times. That doesn't rewrite the slowdown, it complicates the scoreboard. Seismology is honest about these caveats. We infer motion from a sparse network of precise but noisy observations and cross-check with multiple paths and methods. The convergence, repeaters, test shots, arrays keeps pointing the same way. Speed up, slow down, gentle, reverse on a decadal beat. So, does a backtracking inner core mean a dying dynamo? No. The Geodynamo lives in the liquid outer core. The inner core's rotation tweaks torques and may modulate the dance, but it isn't the drummer. Picture a band where the bassist, inner core, occasionally lags the drummer, mantle, by a half beat, because the room acoustics, outer core flow and magnetic coupling changed. The groove feels different. The song still plays. In fact, an inner core that can torque back and forth suggests an engine that's lively, not failing. Energy is still moving, coupling is still strong, and the system is elastic enough to exchange angular momentum without breaking its rhythm. What does tie this to our dent in the sky is timescale. The same decadal variability that nudges the inner core also shows up as geomagnetic jerks, abrupt changes in the rate of change of the magnetic field at Earth's surface. Those jerks ripple through observatory records, hinting that outer core flow reorganized. When it does, reverse flux patches at the core mantle boundary can wax or wane, and the surface field above southern Africa can weaken a little faster. The inner core's backbeat isn't the cause of the South Atlantic Anomaly, but it's part of the orchestra we're finally hearing clearly. Which brings us back to stakes. The slowdown story isn't a countdown, it's a diagnostic. Every decade, the core coughs our instruments catch.
It faster. That makes forecasts less dramatic and more useful. And if the heart still beats, the shield can still scuff. So we head topside, where the dent already costs minutes, money, and patience. The shield has a dent. Inside the South Atlantic Anomaly, stretch a map from Brazil across the South Atlantic to southern Africa, and you're tracing the corridor satellites learned to fear. Operators call it the South Atlantic Anomaly, the SAA. On paper, it's a contour plot of lower magnetic intensity. In orbit, it's the 10 minutes per pass when instruments go dumb, star trackers see ghosts, and memory starts flipping bits like popcorn. Here's the mechanic, not the myth. The inner Van Allen belt, a torus of energetic protons trapped on closed field lines, rides closer to Earth where the magnetic field is weak. Because Earth's dipole is offset from center and tilted, that trap droops lowest over the South Atlantic. A satellite at a few hundred kilometers suddenly flies under the proton ceiling. Sensors designed for photons see particle hail. Error-correcting memory earns its salary. Whatever slips through trips watchdog timers. You see it later as black rectangles in data, planned science outages, because teams would rather lose frames than cook detectors. Hubble has a standing no science zone stamped over this longitude band. The International Space Station watches dosimeters tick higher and shutters sensitive experiments. CubeSats with thrift store shielding learn the hard way. One night, a student on console watches the attitude solution tumble into nonsense as a star tracker feeds corrupted centroids. The code falls back to gyros, reboots clean, survives. Nothing heroic, just standard life under a dented sky. The maps evolved. 2 decades ago, the anomaly looked like one blue bowl on an intensity plot. ESA's swarm satellites stitched a time-lapse. The basin widened, drifted west, then butted a second lobe to the east. That split matters because schedules hinge on minutes. A telescope that counted on a single window now dodges 2. Operators widen masks, shave exposures, and accept losses because the alternative is dead pixels and shortened mission life. It isn't only hardware. Flight surgeons track dose budgets for crews. The SAA isn't a crisis at current altitudes, but it raises the floor. Add a solar storm and the margin thins.
Dispatchers slip polar routes south on bad days and plan EVAs to dodge predicted peaks. In the cockpit over the anomaly, a compass wanders a hair before the avionics vote it down. The system is built for this. Still, the Dent turns routine into overtime. We like our villains clear, but the belt is only the delivery truck. The address is deeper. The surface field over the South Atlantic is weak, because the field at the core, mantle boundary beneath southern Africa, is tangled and in places reversed relative to the global dipole. That reverse flux patch drags the dipole off center and lets non-dipole features grow loud. The mantle piles above, one of Earth's deep thermochemical provinces, modulate heat loss and steer core flow, helping the patch persist. The Dent in space is the last link in a causal chain that starts 2,900 kilometers down. You can watch the fingerprint in real operations. An ocean color imager returns a neat gap off Namibia, masked on purpose. A gamma ray instrument goes safe, then wakes with clean baselines. A ground analyst overlays reset events by longitude. A skewed cluster west of Africa, another east of Brazil, matching the twin lobes swarm mapped. Schedules look like airline timetables. Instrument off at 1312, on at 1326. Every orbit, every day, nudged a little earlier each quarter as the centroid creeps. Altitude and inclination set how hard the SAA bites. Fly lower and drag trims proton energies. Fly higher and you clear the worst. There's a band where flux is just right to be a problem for popular orbits. Insurance actuaries know that band. So do procurement teams who argue for rad hard parts that weigh more and cost more and save missions quietly. One engineer swaps standard memory for a hardened part. The change adds grams and years. No trailer roll, just a flat error log the next storm day. The anomaly breathes with the sun. When a coronal mass ejection squeezes the magnetosphere and pumps fresh particles into the inner belt, the SAA's floor climbs. Teams widen masks and ride it out. This is why you see space weather on the whiteboard next to target lists. The Dent turns a solar forecast into a shift schedule. Here's the uncomfortable truth. The SAA is not waiting for you to finish your design review. It drifts, splits, and surprises. That's not bad news, it's a reality check. Treat it like weather, map it often. Fly with margin, harden what must stay on. Power down what can sleep. Keep a hand on the proton counter and a finger on the mask length, and remember where it starts. The Dent isn't a hole in space, it's the surface echo of magnetic
Weather in a metal ocean under Africa. Deep roots, Africa's reverse flux patch and the mantle's hidden giants. Unknown to most people watching satellites hiccup over the South Atlantic. The mischief starts under southern Africa, at a boundary we can't visit, but can map by listening, and by ESA swarm inverted core field models. On the core mantle boundary, where liquid metal meets hot, solid rock, geomagnetists keep finding a stubborn blemish, a patch where magnetic flux points the wrong way relative to Earth's global dipole. It's not a tiny eddy, it's a continental-scale bruise that refuses to fade. In models that let the dynamo run, that reverse patch doesn't just happen anywhere. It blooms beneath Africa, where the mantle above isn't normal. Seismologists have a nickname for the giants parked there. Large, low, shear velocity provinces, LLSVPs. Two of them, one under Africa, one under the Pacific. They're not magma oceans, but they're hotter and likely compositionally different from surrounding mantle, so seismic waves slow down as they cross. Picture colossal, woolly plateaus slumped against the core, insulating some places while their steep edges leak heat like cracked radiators. That uneven heat loss, the how much and where, is the thermostat for the core's metal weather. Over Africa, the contrast is sharp. At the base of that LLSVP, heat trickles in one patch and pours in next door, setting up shears in the outer core's flow. Fast columns next to slow ones twist field lines into knots. In numerical dynamos forced with African-style heat maps, the same pattern repeats. A reversed flux patch forms beneath southern Africa, migrates, splits, then reforms. Up top, the surface field weakens in a lopsided bull's eye that lines up with today's South Atlantic Anomaly, as mapped by Swarm. The belt sag we dodge in orbit is the end of a story. The core started at that heated rim. This isn't modeling for modeling's sake. Rocks back it up. Archaeomagnetists collect fired clays, Iron Age pottery and hearths from southern Africa and date them carefully.
As those kilns cooled, tiny iron minerals locked in the local field. Layer a timeline of those directions and intensities across centuries, and you get repeated dips, episodes when the field over southern Africa was unusually weak and sometimes pointed askew. Offshore, South Atlantic sediments record the same softness. On the other side of the ocean, the salts in Brazil answer with directions that don't match a tidy bar magnet. Different materials, same theme. This sector misbehaves often. Meanwhile, swarm-class inversions peel off the ionosphere's daytime loops and the magnetosphere's storm surges to reveal the core's baseline. Those maps show reverse flux intensifying beneath southern Africa, riding westward drift and feeding the surface dent we fly through. Seismic tomography stacks, thousands of earthquakes marching through Earth, trace the African LLSVP's bulbous top and steep sides. Put the pictures together and a loop emerges. Deep mantle structure modulates heat. Heat patterns steer core flow. Core flow breeds a reverse patch. The surface above weakens. The inner belt droops. Satellites feel it. There's still a fight over identity. Is the African LLSVP mostly hot, or also chemically distinct enough to be denser and long-lived? The answer matters for timelines. A purely thermal blob might evolve faster. A thermochemical pile could persist for hundreds of millions of years, making its magnetic influence a recurring character in Earth's story. Right now, the best fit is both. A long-lived pile with thermal hills and valleys that wax and wane. That mix would explain why the reverse patch keeps coming back under Africa while still breathing on decadal scales. The models also explain why this neighborhood matters in reversals and near misses. When dynamos flip in simulations, big reverse patches often grow first at LLSVP margins, eroding the dipole until the field goes multipolar. Extra poles sprouting at odd latitudes before reorganizing opposite. Earth's record shows excursions like Laschamp, a dramatic weakening without a full flip. Southern Africa shows up there too, an early stage where weakness concentrates. Not a guarantee, a habit. The human part looks small and precise. In Cape Town, a grad student carries sherds from a dig to a shielded room, heat treats them in tiny steps, and watches magnetization curves hold steady at low intensity. Across town, a modeler nudges the heat flux at the African LLSVP's edge and watches a reverse patch in their simulation wrap farther around the core. They tape plots side by side, clay and code, and write close in pencil. That one word is how disciplines meet. The stakes are practical. If the African patch is a persistent engine for surface weakness, the SAA isn't a one-off. It's the present face of a long pattern. It will drift, split, and surprise, but it probably won't vanish on a schedule we prefer. That doesn't mean
Panic. It means treating magnetic complexity like weather. Keep the core maps fresh, harden what must stay awake, mask what can sleep, and remember the causality. The dent is a surface echo. The source is a giant, lumpy blanket under Africa, telling the core where to race and where to rest, and telling us how to fly.